Good morning, physics class. It's coming to the end of the year, but I hope that you're keeping up with everything. And welcome to another day of physics class. Today we're going to be working on starting with speed of sound and moving on to some review questions to prepare you for this week's quiz and as we come to the end of the year. So here we have free body diagram. The gun is fired and the projectile heads, and for all intents and purposes we're going to make it going away from the observer who sees the gun fire, and then hears it 12.5 seconds later. How far is this great hunter from the observer? The speed of light is 3.00 times 10 to the 8 meters per second, and the average speed of sound is 350 meters per second. Just so you know that varies. The speed of sound varies on some variables. Also, the speed of light can vary depending upon the medium in which it's passing through. So, if we start off with our speed of sound as 350 meters every second, and it took 12.5 seconds in order for the sound to reach the ears of the observer. It just becomes a simple matter of unit analysis to find out how many meters the observer is away from the gun being fired. We get 4,375 meters. If we put the two significant digits in, we would have the distance as being 4.4 times 10 to the third meters, or 4.4 kilometers. You could put also, or you could put 4,400 meters. I'd accept all those answers. Now, this is not part of the question, but again, I wanna just kind of look at this. If it is 4,375 meters, and the formula unit is 3 times 10 to the 8th meters per second, I can use a reciprocal value in order to get the time that the light would take to get to the observer. So we could do 4.375 divided by 3 times 10 raised to the 8th power, and we get a grand total of that would take 0.0001458 seconds. So if you think about it, that would be 1/100th of a second for you to see it, while it takes 12 seconds for you to hear it. Difference in speed of sound and speed of light. All right, let's move on to our next question. It says, find the heat necessary to raise the temperature of 2.5 kilograms of ice at 0.75 degrees Celsius to steam at 100.25 degrees Celsius. One of the things that you'd want to use in order to is the specific heat chart that I provided you with. I believe it was last week, and that'll help us determine how much heat energy it takes in order to convert this ice to steam. So the first thing we'll do is we'll start out with ice. Ice has a specific heat of 2050 joules per kilogram degree Celsius. If we are raising it 0.75 degrees Celsius and we have 2.5 kilograms, we can just use a little bit of unit analysis to find the amount of energy it takes to raise the temperature of the ice. So we'll take 2050 times 0.75 times 2.5. I'm not going to get a very big answer relatively to what else we're going to get. So we're going to get 843.75 joules. And then we're going to find the amount of energy it takes to melt the ice. The latent heat and fusion value for water is 334,000 joules per kilogram. And there are 2.5 kilograms. So the kilograms will cancel. We'll take our 334,000 and multiply that by 2.5 kilograms of ice. When you can see we're going to get a whole lot more energy for this. 835,000 joules. Now we're going to raise the temperature of the water. Specific heat of water is 4,186 joules per kilogram degree Celsius. The fiducial points of water are 0 and 100, so the difference between them is 100 degrees Celsius. And we were given in the problem that we have 2.5 kilograms of water. So we can multiply all those values together, 4,186 times 100 times 2.5. And we're going to get 1,046,500 joules. Now we're going to find the big one, boiling. And when we boil, the latent heat of vaporization is 2,256,000 joules per kilogram. And we have 2.5 kilograms of water that we want to boil. So we will take our 2,256,000 and multiply that by 2.5, and we're going to get 5,640,000 joules just to boil the water. And then we want to change the temperature of the steam. The specific heat of steam is 2,009 joules per kilogram, and we have 2.5 kilograms. So we'll multiply 2,009 times 2.5. Times degrees Celsius. I almost forgot about that. Excuse me, it doesn't want to write where I want it to write. Okay. Times 0.25 degrees Celsius gives me 1,255.625 joules. And then we'll add those up. 5,640,000 plus 1,046,500 plus 835,000 plus 3,843.75 gives me a grand total of 7,526,599.375 joules. All right, then if we were looking for the answer that we're going to leave on the test or homework, we have two significant digits found right there. So we're going to say 7.5 times 10 to the 6th joules. All right, let's move forward. The next question we have is in the simple circuit shown. I didn't show a simple circuit, so let's make one. Very, very simple circuit. Honestly, I wish we could do more with this type of stuff through, keep going on with physics class, but we have 14.5 volts, and it's passing through a resistor of 250 ohms, and we want to calculate the current passing through there. And so we have volts equals amps times ohms, or V equals IR. So what we could say is we have 14.5 volts. We're looking for the amount of amps, and we have a 250 ohm resistor. So we'll take 14.5 and we'll divide by 250, and we're going to get 0.058 amps is our current. And then we're going to take our current to find out how many electrons. Well, an amp is equal to a coulomb per second. So we could say that we have 0.058 coulombs going past every second. And when we look at this, we know that a coulomb is 1.6 times 10 to the negative 19th coulombs is equal to 1 electron. Okay, so we can use that in some unit analysis to find the electrons per second. Okay, so we could take our 0.058 coulombs per second, and then we'll say 1.6 times 10 to the negative 19th coulombs is equivalent with 1 electron. So now we just do the math. 0.058 divided by 1.6 times 10 raised to the negative 19th. We're going to get 3.625 times 10 to the 17th electrons every second. So my solution that I could come up that I'm going to leave with applying my 2 significant digits found right there is going to be the current is 0.058 amps and the electron value passing every second is 3.6 times 10 to the 17th electrons per second. All right, that's how we're going to do that problem. Let's move on to our 4th problem today. It says a hollow sphere is tethered to the ground, and being tethered to the ground underwater, there's buoyant force pushing up on this sphere, and so that's going to cause there to be tension in the rope because this thing would float, and so we're going to find the amount of tension found in the rope. So in my free body diagram that I'm putting together here, I have buoyant force is pushing up, weight and tension are holding it down. So there's some things that I want to pay attention to as I begin here. The first one is that volume of a sphere is 4 pi r cubed over 3. Obviously, if this was a rectangular prism, we'd use length times width times height like we have in other problems. So as I look here, I would need to find the radius. It says the radius is 4.5 meters. It says radius and it says meters, so I don't have to convert anything. It's good. It's nice that your teacher didn't put that in feet or something for this particular problem. So we're going to have V equals 4 pi times 4.5 cubed over 3. So according to order of operations, I'm going to cube the 4.5 first to get 91.125. I'm going to multiply that by 4 and pi and put that over 3. So again, we'll multiply by 4, then we'll multiply by pi, and then we'll divide by 3. Pretty close. One of the things in estimating this, because I like to estimate things also to make sure that I'm getting close to the answer. The pi is are close to canceling. So then I think, what's 90 times 4? Just an estimation, 360. So therefore, I'm going with my answer, kind of a double check just to make sure that I'm in an okay situation. And I probably should erase that so when you look at the inks, you don't think I just canceled out the pi's, because that's not what I did. All right. And so now what we're going to do is we're going to use Archimedes' principle. And Archimedes' principle states that the buoyant force is equal to the weight of the water or liquid displaced. Okay, so what I want to calculate is I want to calculate the weight displaced. So I'm going to start with the density of water, and this is salt water, and I'm also going to apply the volume, and I'm going to apply gravity to my unit analysis. So let's begin looking at how we're going to do this. The first thing that we have is the density of salt water. It's 1,025 kilograms per meter cubed, given right here. And then we have the volume that we just calculated at 381.7035 meters cubed. And then gravity is 9.81 newtons per every kilogram. So meters cubed cancels, kilograms cancel, and all I'm left with is newtons. So we have 1,025 times 381.7035 times 9.81 equals a buoyant force, or the weight of the water displaced, because that's what we're calculating as weight, is, let's see, 3,838,124.118 newtons. But that doesn't tell me the tension. We're looking for the tension. In order to find the tension, we're going to say the sum of the forces in any direction is mass times acceleration. Newton's second law of motion. And so over here in my free body diagram, I have the forces that are acting on the system. I have the positive buoyant force, I have the negative tension, and I have the negative weight, mass times gravity. And that's equal to mass times acceleration. This is not accelerating. It's not moving up. It's staying in one position. So we can zero out the right-hand side, and we'll say 3,838,124.118 minus the tension minus the mass, which was 3.25 times the gravity of 9.81. All right. So I'm going to move the tension to the other side because it's negative here, and I can just use simple algebra to move it to the other side. And I'm going to say 3,838,124.118 minus, and I'm going to work this out on my calculator. 3.25 times 9.81 is 31.8825. In working this out, I made a very, very big hollow sphere, 4.5 meter radius. You think about this thing, this ball would be huge underwater. That's why we have such a big buoyant force. So we're going to take our 300. Honestly, I hope you're seeing what I'm seeing. When we begin applying significant digits, the 31.8825 in this particular case has very little bearing on the problem, because I'm going to get 3,838,092.236 as the tension. So by the time I put the three significant digits into the problem, in this case, because I made it such a huge sphere when I was setting up this problem, the the weight of the sphere doesn't play too much into the solution of the problem. So it's 3.8 times 10 to the 6th newtons is the tension in the sphere. All right. Hope you learned something from today's lesson and this review, and keep on working on your homework. You're doing good. Most of you are turning in your stuff and working really hard. I am very proud of the class.